Hello science fans, here is a video on nuclear radiation, which is for your GCSE Physics Paper 1. Let's start with talking about nuclear decay, or radioactive decay. Some nuclei are naturally unstable and they emit ionizing radiation in order to become stable. It's important that you know that that process is completely random. So if you have to describe it, it is a random process. Ionizing radiation, well, that means that the radiation is able to remove electrons from atoms, and that can have all sorts of consequences for things like DNA, and it can cause things like tumours. Something you need to know about decay is that we can measure it, and we measure it by looking at the number of decays per second. The number of decays per second means the number of nuclei that have decayed in that 1 second, and we call that the activity. And we measure it in becquerel, and the symbol we use is BQ. There's a device we use to measure that called a Geiger-Müller tube, and on the Geiger-Müller tube it will give you a number, and that number tells you the activity or number of decays per second. Okay, next thing you need to know about is about the different types of ionizing radiation. So here we go. We've got alpha radiation, which is a particle, and there's its symbol. An alpha particle is 2 protons and 2 neutrons, which is the same thing as the nucleus of a helium atom, as though all the electrons have been stripped away. It's got 2 protons, so it's got a charge of 2+. It's highly ionizing. Well, it would be. It's got a charge of 2+. But it can only travel about 5 centimeters in air, and it won't pass through paper or skin for that matter, so it can be stopped by those things. Beta radiation is also a particle. It's just a high-speed electron that's emitted from the nucleus during decay. It's not the electrons that sit in the shells around an atom. It's also quite ionizing. It has medium ionizing power because it's charged. But it can travel a little bit further in air, perhaps 10 or so centimeters. It will pass through paper and skin, but it's stopped by thin metal foil. Gamma radiation isn't a particle at all. It's an electromagnetic ray, so it's just like light. It's just a much higher frequency. Its ionizing power is actually low because it doesn't have a charge, but just now and again it can hit an electron and give it enough energy to remove it from an atom, which does ionize the atom. Its distance it can travel is infinite. We measure gamma radiation from the other side of the universe. So unless it gets stopped and absorbed by something, its distance is infinite. We can stop it using protection of a lead sheet. Let's just talk about those 3 in terms of dangers, because you might be asked about that. Well, alpha particles won't pass through your skin, but they are highly dangerous if you swallow them or breathe them in because they're so ionizing. They will interact with atoms in cells and cause a lot of damage, killing cells and possibly causing tumours. But they only travel about 5 centimeters in air, so it's quite difficult for them to get to you. So remember, unless you breathe it in or swallow it, there's very little danger from that. Beta particles will pass through your skin, and they are quite ionizing, so they do have those same risks associated with them if they get into your body. Again, if you swallow them and breathe them in, you're in real trouble, but they can also get in through your skin. Finally, we have gamma radiation. That will pass through your skin and also passes through everything else in your body. So it just passes in through one side and straight out the other, and is highly unlikely to actually interact with the cells in your body. But if it does, it can cause some damage, but it makes it less dangerous than alpha and beta. Okay, whilst we're talking about dangers, we need to know about contamination. So contamination, a radioactive contamination, it means the unwanted presence of radioactive materials on other materials. For example, a slice of cake. So here we've got a slice of cake, brilliantly drawn by me, and you can see the little pink spots. That is radioactive material. That means it is emitting either alpha, beta or gamma radiation. That is very dangerous because if you swallow it, that means that those things are now inside you emitting radiation into your cells. Because the cake's contaminated, it's touched the source of radiation, the cake itself is now radioactive. So wherever you take that cake, it will appear to be radioactive. Irradiation, the other type of exposure to ionizing radiation, is just where an item is exposed to the radiation, but it doesn't touch it. So it's exposed to the source, but it doesn't touch it. In this case, our slice of cake has been exposed to a source of perhaps gamma rays, but it hasn't actually touched it, so there's no radioactive atoms actually on that cake. That means the cake is not radioactive, and it's much less dangerous. You could quite safely eat that cake afterwards, and in fact we use this method to kill bacteria on things like fruit, so actually it might be slightly safer than before it was irradiated. Okay, number 4, so which is the most dangerous here? Well, of course, something that's contaminated with alpha radiation is the most dangerous, because alpha radiation is highly ionizing. So if you eat a piece of cake with alpha particle or an alpha emitter source on it, that means that you have eaten something that's highly ionizing and is very dangerous. If you've eaten something that's contaminated with a gamma emitter, or gamma rays are more likely to just pass straight out of your body and much less likely to cause you any harm. So alpha is the most dangerous and gamma is the least dangerous if swallowed. Okay, number 5, nuclear safety. If you're working with radioactive materials, the first thing you do is you use a source with the lowest level of activity. In hospitals and the like, they do use radioactive sources, so they use the lowest possible activity rate. That means it's less radioactive. You use it for as short a time as possible, and you wear protective clothing such as a lead apron or gloves, and also no bare hands, so you might use things like tongs to move the samples around. Let's move on to half-life. Students often find this confusing. All half-life means is the amount of time it takes for the activity to drop by 50%, or for the amount of time it takes for half of the radioactive nuclei to decay. It's often shown as a graph like this. So the way the graph usually works is you're given either the number of nuclei or the activity on the y-axis, and on the x-axis it's time. You look at the starting rate, wherever the top of the line of the graph is, and if you want to find the half-life, you take that number and divide it by 2, in this case 80 becomes 40, and you look at 40, the number that's halved, on the y-axis. You draw a line across to where it meets the curve, and you draw a line carefully down to where it meets the x-axis, and whatever that reading is there, that is the half-life of that sample. So again, half-life, the amount of time it takes for the activity level to drop by 50%, or the amount of time it takes for half of the radioactive nuclei to decay. It's exactly the same thing. Sometimes you might be asked to calculate a half-life, and the way these work is you might be told that something has a count rate or an activity of 800 becquerels to start with, and ends up at 200 becquerels. All you do is you write the start number, and you keep writing half that number until you get to the other number you were given. So 800, a half of that is 400, and a half of that is 200. And those are the two numbers we would have been given in the question. The gap in between each of those is one half-life. So for example, the activity drops from 800 becquerels to 200 becquerels after 2 half-lives. And you might be told that that overall time took 1 hour, in which case you would say, well, 1 hour was 2 half-lives, so 1 half-life must be half an hour. The last thing that we need to cover on nuclear radiation are decay equations. They look really complicated, but they're not too bad at all. There's one golden rule for these, and the golden rule is the top line has to balance and the bottom line has to balance. So, for example, the top one we have alpha decay, and it's called that because it involves an alpha particle here. And we've got an element here. You are never expected to remember either of these two. They are just given to you on the page. You do not need to be able to name them. And all you do is you work out the numbers so it all balances up. It might be that you're not given that number, for example, or you might not be given the bottom number there. All you have to do is fill in the blanks by making sure that 233, whatever that top number is on that side, adds up, those two numbers add up to that number. And on the bottom it's the same. You make sure the numbers all add up so it all balances. Beta decay is just the same. It's slightly more complicated because the number here is -1. But again, it's just a case of making sure all the numbers add up. So here you can see 6 on one side, 7 minus 1 on the other is also 6. You are expected to know the two that are in red. You're expected to know that that's an alpha particle, and you're expected to know that that's a beta particle, and you're expected to remember those numbers. Like I said, you're not expected to know any other numbers for any other elements. Okay, there you go. Nuclear radiation.